So it's a great pleasure to be here. So let me discuss in this relatively recent applications of tropical geometry to a couple of irreducibility problems. So this is a series of joint works with Carl Christ and Shang He. So some are available on arXiv, some are still in preparation. So let me start. Okay. So here is the plan. So we'll give a very brief introduction to the topic. Then I will remind some basic stuff about parameterized tropical curves and about the moduli spaces of parameterized tropical curves. Then I will talk about tropicalization for single curves and for families of curves. And then I will give you a proof by example that will illustrate how you apply the techniques that I will discuss in order to prove irreducibility of certain parameter spaces in algebraic geometry. So, and please interrupt me as much as you need. So any questions are very welcome. So don't hesitate to stop me and ask questions. So let us start. So we'll start with the introduction. And in this talk, we will be interested in the irreducibility property of the following spaces. So the first space is just the classical moduli space of genus G smooth integral projective curves. So MG. The most famous one. The second space is the Hurwitz scheme, HGN, that parameterizes genus G degree n simple branch coverings of P1. And third space is the classical severe variety, VDG here. It parameterizes integral plane curves of degree D and geometric genus G. So of course, in degree D, the arithmetic genus is some function of D, D minus 1 times D minus 2 over 2. But if the curves are singular, then they have smaller geometric genus, and severe varieties parameterize precisely such curves. And more generally, of course, one doesn't have to stick to the plane. So we will talk about severe varieties that parameterize geometric integral curves of geometric genus G in linear systems on toric surfaces. So given a lattice polygon delta, one can associate to it a toric surface and an ample line bundle on it that replaces the notion of degree in the planar case. And you can look at the curves in this linear system. And again, you have some prescribed arithmetic genus for a given linear system, but you want to fix some number that is smaller than the arithmetic genus, and you want to consider the curves that are in this linear system, irreducible curves, of course, reduced, and of this geometric genus. Now, there is also this notion of torically transverse. This means that the curves do not pass through zero-dimensional orbits. So in a sense, they are in general position with respect to the toric action on or torus action on the surface. Okay. So these are the spaces, and let me start with some prehistory or history, depends on what you define to be prehistory. So I'm the first person to ask questions about irreducibility or rather connectedness, because the space was not quite a space; it was more like a set with some maybe topology at best. Was Felix Klein in 1882, and he proved that MG is in fact connected. And to achieve this, he considered coverings of the Riemann sphere. In the modern language, he considered Hurwitz spaces, Hurwitz schemes of certain type, and showed that they are connected and they dominate MG, and as a result, MG is connected. Okay. Now, in 1920s, Severi was interested in obtaining an algebraic argument, because the algebraic geometry has developed, and he wanted to get an algebraic argument that would prove the assertion of Klein about the reducibility of MG. And well, he had several arguments. So one of them was via Severi varieties. And the idea was that Severi variety, classical Severi variety, for large enough degree dominates MG. And therefore, once you know that it is irreducible, you deduce that MG is irreducible. So, but Severi's argument was wrong. Kind of the idea was correct, but the technical details were insufficient. So, in fact, there was a gap in the proof. Now, the reducibility from the analytic point of view was achieved by Teichmüller in 40s, who developed what we call Teichmüller theory. He showed that MG is dominated, analytically dominated by wall. Okay, so it is irreducible. Now, algebraic treatment, or kind of algebraic treatment of irreducibility was really done in 1969 in two independent works. So one is by Fulton, who introduced these Hurwitz schemes formally algebraically, and proved that under certain assumptions on the characteristic, these schemes are irreducible. And since they dominate the moduli space, it follows that the moduli space is also irreducible. Okay. And in the same year, Deligne and Mumford introduced the notion of Deligne-Mumford stacks, again in an attempt, or at least it was advertised as an application to prove the irreducibility of MG, and they did it in any characteristics. So they reduced the problems in the moduli stack of curves is defined over the integers. So they reduced the problem to the characteristic zero case, applied Teichmüller theory, analytic methods in characteristic zero, and obtained the reducibility in any characteristic since the moduli stack is smooth. Okay, and of course they had to consider compactification, not just smooth curves, but what is called stable curves. So they had first to compactify MG to run all these reduction arguments. So, in a sense, the reducibility of MG was settled by Deligne and Mumford, but it used analytic methods in characteristic zero. So in 1982, Fulton managed to get rid of these analytic arguments based on another work of Mumford in Paris. And he ran some inductive argument on compactification so forth with schemes to prove, at least in characteristic zero, that in an algebraic fashion, that the moduli space is irreducible. And then the argument of Deligne and Mumford implies you get an algebraic treatment still via reduction to characteristic zero of the reducibility of MG. And finally, Joe Harris in 1986 proved irreducibility of the classical Severi varieties in characteristic zero. So it was a big achievement because many people were interested in this problem. Fulton, Zariski, Harris, and others, and it's quite an amazing proof, rather involved, and it is strictly restricted to characteristic zero. It does not work in positive characteristic. Okay, so this is a prehistory, and now let me just state the main result and discuss the strategy of the proof to conclude the introduction with this strategy. So the goal of today's talk is to explain how to prove the reducibility of all these spaces in arbitrary characteristic via tropical geometry. Okay, so these are relatively new methods, so they were not at the disposal of previous authors. So, in fact, they allow you to prove the result in any characteristic directly without need to do any reduction on characteristic or any analytic methods, whatever. Now, with the last space in these severe varieties on toric surfaces, one must be slightly careful because sometimes they are reducible, so you can't prove that they are always irreducible. And there are examples where the behavior depends on the characteristics, so one must be slightly careful. So one must restrict the type of surfaces, toric surfaces you consider. So let me just give you two remarks and that explain the relation between things. So the first remark is that it is not difficult to check that in fact the moduli space MG and the Hurwitz schemes, they are both dominated by certain Severi varieties. Okay, so you must consider Severi varieties on certain toric surfaces, for example, Hirsebruch surfaces are good enough. And then you can dominate MG and HGN with the Severi varieties. Therefore, once you know the irreducibility of Severi varieties, you know the irreducibility of other spaces as well. So we will, in fact, restrict our attention to the Severi varieties, the varieties that parameterize curves in the surface, the toric surface, given linear system on a toric surface, and of given geometric genus. And another remark I already mentioned is that sometimes these V delta G here, they are in fact reducible, so one must be slightly careful. So the methods that we develop, they have their limitations. So they are rather general, they cover more than the main result that I'm going to formulate, but they still have some limitation due to quite a lot of combinatorics, and not only combinatorics, but also arithmetics that is involved. So we will not see arithmetics today, but we will see the type of combinatorics that is involved. Okay, so here is the main result that we'll discuss, and it says the following. So the Severi varieties on the projective plane, on the Hirsebruch surfaces and on smooth toric Del Pezzo surfaces are always either empty or irreducible, and this is independent of the characteristic. So you can work in your favorite characteristic if you like 2, 5, or 0, and you can prove that Severi varieties are irreducible in all these cases. In fact, in more cases, so the proof by example will be for a different surface, but at least in these cases. And as a corollary, you immediately get the irreducibility of Hurwitz schemes in any characteristic. This was not known. And so the irreducibility of Severi varieties in positive characteristic was also not known. And as a benefit, you also get the first proof, direct proof of the irreducibility of MG that involves no reduction to characteristic 0. Okay, so this is kind of the main result that I would like to present today.
But this is the Hurwitz scheme, just I mean, there is no degeneration of the curves involved in this Hurwitz scheme, right?
Yes, yes.
Okay.
But in fact, they will be hidden somewhere because we will work over a non-Archimedean field. So there will be some degenerations hidden somewhere, but we will not see them.
I guess my question was that it could still be that if you have like admissible covers of nodal curves, that there are extra components showing up.
Yeah. Yes, so okay. This is true. And also kind of the question, how you define Hurwitz schemes. So there are several ways to try to define them. And in some ways, you will immediately get several components. But if you define them most naively, kind of simple branch coverings, okay, just over a field of given characteristic, then with this definition, they are irreducible. Okay, good. So let me describe the strategy of the proof and to conclude the introduction of the strategy. So, and to do this, let me introduce some notations. So assume that we are given some irreducible component of a Severi variety, okay? And now we work over a non-Archimedean field so that I can freely talk about tropicalizations of things, okay? And I have this tropical counterpart of the algebraic statements. So let V be an irreducible component, and let us pick some curve parameterized by V, okay, some C in V. And let us consider the natural map from the normalization of this curve to the toric surface. Then this map admits tropicalization. So I will remind briefly what tropicalizations are later on. So I hope that everyone is more or less familiar with this notion. So, but if not, just wait for formal introduction. So there is some way to produce a tropical object associated to a morphism from a smooth curve to a toric surface. Okay. So now for such a tropical curve, I can look at its combinatorial type. So kind of discrete datum behind this tropical object. Okay. And I denote by CTV, so combinatorial types associated to V, the set of all combinatorial types of tropical curves obtained this way. Okay, so this is a notation. So I look at an irreducible component, I look at curves it parameterizes, I look at their tropicalizations, and I collect all possible combinatorial types of these tropicalizations. And now the strategy of the proof is the following. So the first step is to produce one particular type that is represented by a unique component. Okay, so that it belongs to CTV for a unique component V. In fact, this is not very difficult. This is some deformation theory, but it's not very difficult. In many cases, so in all the cases covered by the theorem, it's not very difficult. And then step 2 says that, well, pick this particular type and try to show that it necessarily must be contained in CTV for any irreducible component. If this is the case, then there is only one irreducible component. Okay, so these are the 2 steps. So I identify one component with a particular combinatorial type of tropical curve that comes as a tropicalization of a curve from this particular irreducible component. And then I show that, in fact, any other irreducible component must contain a curve with this type of tropicalization. So any other irreducible component has to coincide with the very first irreducible component that I picked. Okay, so this is a strategy. So are there any questions about the problem, the strategy, where we are going now? Okay, good. So if there are no questions, let me proceed. But again, if you have any questions, just interrupt me. Feel free to interrupt me and ask. So let us talk a little bit about parameterized tropical curves and modeling spaces. So I assume that more or less everyone is familiar with these notions. So I briefly remind these things just to be on the same ground with everyone. So let me start by recalling that a tropical curve, a reducible tropical curve, is just a finite connected graph with marked ends, okay, gamma e, so I always mark the ends, equipped with 2 functions, length functions. So for each edge, I have a length, which is a positive number or infinity, and the genus or weight function, g, from the set of vertices to the non-negative integers that satisfies the following properties. So first of all, the length is infinite if and only if the edge is a leg. Okay, and second, the valency of any vertex of genus 0 is at least 3, and of any vertex of genus 1, it must be at least 1. So this is, of course, the shadow of stability condition on the algebra geometric side. Okay, so now the genus of a tropical curve, gamma, is defined to be the first Betti number of the graph, so the number of loops in the graph, plus the integral of the genus function of the vertices. So some genus can hide in the vertices and some genus in the dual graph, in the graph of the tropical curve. Okay, so this is the notion of an abstract tropical curve, and the parameterized tropical curve is the following conjugate. It's just a tropical curve gamma e together with a piecewise integral affine map to a linear space that satisfies a certain balancing condition. So what is the balancing condition? If you take any vertex and you sum up the slopes of h along the edges adjacent to this vertex and pointing outside, away from this vertex, then you want this sum to be 0. So since h is piecewise integral affine, all these partial derivatives, all these slopes are integral vectors. They need not be primitive integral vectors. So in some classical texts, people consider just primitive integral vectors and multiply them by certain multiplicities, but the multiplicity is hidden inside the derivative. Okay, since piecewise integral affine map may have non-primitive slopes. Okay, so now the collection of slopes of the uncontracted ends is called the degree. And the discrete datum of the parameterized tropical curve is called the combinatorial type of the tropical curve, of the parameterized tropical curve. So the discrete datum consists of the underlying marked graph with marked ends, of the genus function, And so genus has integral values, so it doesn't vary continuously. And of the slopes, and the slopes are integral vectors, so they don't vary continuously either. The rest, the position of the vertices, the images of the vertices, and the lengths of the edges, they do vary continuously. So this is a continuous piece of datum, which is unrelated of the combinatorial type. Okay, good. So there is a particularly convenient type of tropical curves, of parameterized tropical curves, that we will use. And these are curves introduced by Brugalet and Mikhalkin, and they're called floor decomposed curves. So here is the definition. So a parameterized tropical curve H from gamma to R2, so this is for planar curves, is called floor decomposed if it has slopes either plus minus 1 comma something or 0 comma something. So the slope must be either vertical or must have a horizontal component plus or minus 1. So, and here is the picture of such a curve. Okay, floor decomposed. This is a planar cubic, a rational planar cubic, floor decomposed one. Okay, and each floor decomposed curve comes with consists of two types of pieces. So one piece is called elevators. So these are the vertical edges and legs. So in this case, we have one elevator here, one elevator here, and three unbounded elevators going down. Okay, and floors. So floors are all the rest. So in this case, we have three floors. So this is the top floor, and the middle floor, and the bottom floor that are joined by these elevators. So you can think about it as you have floors and you have elevators going between them. And in fact, we will play this game with elevator between floors and traveling up and down several times later on. Okay, so this is the notion of floor decomposed curves. Now, as I already mentioned, they were introduced by Brugalet and Mikhalkin. And Brugalet and Mikhalkin in particular proved that if you pick points in vertically stretched positions, so vertically stretched means that the distance, the horizontal distance between the points is much, much smaller than the vertical distance. And you pick the right amount of points. So here I write this remark for planar curves, for degree D curves, but it is true for in larger generality, not only for planar curves. And then all tropical curves of given degree and genus passing through this vertically stretched collection of points must be floor decomposed. They must be trivalent, they must be weightless, so their genus function is in fact 0 on the vertices, so the whole genus is inside the first Betti number of the graph, okay? They must be regular, so they vary in the family of expected dimension, okay? Floor decomposed, and furthermore, each floor and each elevator must contain precisely one of these vertically stretched points, like in this picture. You can see that on each elevator and on each floor, we have exactly one such point. So in the case of, so this is rational cubic, so there must be 8 points. This is precisely what we have here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Good. So now let me remind you the notion of moduli spaces of parameterized tropical curves and describe a couple of strata that I will be interested in this talk. Okay. So if you look at the isomorphism classes of parameterized tropical curves of given degree and genus, then they form a nice moduli space. Okay, this moduli space admits a natural structure of what is called generalized cone complex. So it doesn't really matter what these words mean. So it is glued from polyhedra, okay, where some are bounded, some are unbounded. Okay, with each polyhedron comes with its integral structure in a natural way. Okay, and these polyhedra, these open cones, they are parameterized by the combinatorial types. Okay, the coordinates in each polyhedron are precisely the continuous parameters that we have in the definition of a parameterized tropical curve, and the polyhedron itself is labeled with the combinatorial type, which is fixed within this, the given polyhedron. Okay, and we will be interested in the following two special types of polyhedra, of these open cones in the moduli space of parameterized tropical curves. So here are the types. The first type is called nice, and it is regular, so it means that it has expected dimension, and the underlying graph must be weightless. The genus function on the vertices must be 0, and it must be trivalent. Okay, so these are the nicest maximal dimensional cones that we have in the moduli space. So there may be some cones of superabundant dimension, they are not nice. Okay, but the maximal cones of expected dimension, these are precisely the nice cones defined here. And the second type is the simplest possible degeneration of nice cones. So the the codimension 1 boundaries of nice cones, and these are called simple walls. So these are cones that they are also regular, so they also have expected dimension. They are also weightless, so the genus is concentrated, the whole genus is concentrated in the graph, not in the vertices. And the last requirement is that they are almost trivalent except for a unique 4-valent vertex. So this is what happens when you take one particular edge and you shrink it to length 0, and you, instead of 2 3-valent vertices, you get 1 4-valent vertex. So these two types of cones, they will play a central role in the talk today. Okay, so here is an example. So assume that we are considering a rational curve, genus 0, parameterized tropical curves with 4 marked ends, okay, and degree plus minus E1 plus minus E2. So 1 ray in the positive x direction, 1 in the negative, and the same with the y direction. So then the moduli space of such curves, okay, up to a translation, this R2 times is responsible for translations. So it looks like a tripod. Okay, so the blue ray here parameterizes curves that are pictured here, schematically pictured here. The purple ray parameterizes curves that are schematically pictured here. Okay, the image is pictured here. The brown ray parameterizes curves with a contracted edge of varying length. So again, we have a nice cone whose image looks like just a curve with a 4-valent vertex, but we're talking about parameterized tropical curves, and the parameterization is 3-valent, like in this picture. And these 3 cones are joined at a vertex that indeed parameterize curves with a unique 4-valent vertex. Okay, so this is a simple wall, kind of R2 times this red vertex is a simple wall, and these 3 times R2, they are nice cones in this baby example. Okay. Any questions? Okay, good. So then let us discuss a little bit tropicalizations. So, and for tropicalizations, we will work over the algebraic closure of a complete discretely valued field. So the field itself is not discretely valued, it's algebraic closure, so the valuation is admits rational values. You can think about the field of Piso series if you wish, or any other field of pure or mixed characteristic, it doesn't really matter. So given a smooth integral projective curve with n marked points, CP, one can tropicalize it. This means that one can associate to it a tropical curve gamma E. There is a well-established procedure. So, and this procedure satisfies the following 2 properties. First of all, if the tropicalization preserves the genus, so the genus of the original curve is equal to the genus of the tropicalization. And second, everything in the tropicalization procedure can be described explicitly in terms of the stable model of our curve with marked points. Okay, I will not do it because it will take me too much time. So I hope that you're familiar with this tropicalization procedure, but if not, then just get it as a black box. It is absolutely fine. You will not need the knowledge of how this procedure works. Okay. Now, if in addition you have a morphism from the complement of your marked points to an algebraic torus, then you can tropicalize also this morphism, and you obtain a parameterized tropical curve, trop f from gamma to the tropicalization of the torus, which is just the linear space RR. Okay, and again, this procedure is well established. It is very explicit. Okay, everything can be phrased in terms of the stable model and in terms of the monomial functions on the algebraic torus. If you're not familiar with this procedure, just believe that there is such a procedure, and this is sufficient for the purpose of this talk. Now, I would like to discuss the tropicalization of one-parameter families. So assume that now we are given not a single curve, but we are given a one-parameter family of curves with marked points. So the base of our family is an irreducible algebraic curve with some marked points, BQ. And over it, we have a family of curves, a family of curves with marked points, CB, PB. And moreover, we assume that we have a morphism from the complement of the marked points PB in CB to an algebraic torus. Okay. So we want to understand what would be a tropicalization of such a family. So what one would like to have is a tropicalization of such an object. The reason I'm interested in one-parameter families is twofold. So first of all, it is sufficient for the proof. And second, for one-parameter families, we have a pretty well understanding how the tropicalization of the base looks like. If you work with the high-dimensional families over a base of high dimension, then it is not quite clear what we would like to have as a tropicalization of the base, okay, in general. So, but for curves, it's kind of clear. So now let me just state one possible way to think about the tropicalization, and it is the following. So the tropicalization of a one-parameter family as above is a tropical map from the tropicalization of the base to the moduli space of tropical curves that commutes with fiber-wise tropicalization. So if I tropicalize a point in the base and look where alpha takes it, I get some isomorphism class in the moduli space. And I want this to be precisely the isomorphism class of the fiber over this point. Okay. So this is the requirement, and I want this for all points but the marked points. Okay. So the natural question is, can we tropicalize one-parameter families? And one must be slightly careful because, I discussed tropicalization of curves only for smooth curves. And in a general family, the fibers are not smooth, and also the base curve is not smooth. So in this generality, perhaps the answer is no. Or at least one must give some meaning to this tropicalization as a generality, but one can modify the family slightly, and then there is tropicalization in this sense I described here. Okay, so here is the tropicalization theorem, the main result. So if you replace your base of the family with an appropriate finite covering, mark more points. Okay, sometimes you must mark more points on the base, and replace the family with a nice model, with an appropriate model. Once you do it, you can tropicalize the family. So there is a tropical map from the tropicalization of the base to the moduli space that commutes with pointwise tropicalization. So now notice that the words tropical map, they hide inside non-trivial information because it's not set theoretic map. Trop BQ, tropicalization of the base, is a tropical curve. It has a piecewise integral affine structure. The moduli space is a tropical space. It has a piecewise integral affine structure. This map must respect these structures. So when I say that there is a tropical map alpha, it is much more than just set theoretic map. Okay, and the claim is that there is such tropical map that commutes with pointwise tropicalizations, or if you wish, of course, set theoretically, this map is defined just by requirement that it must commute with pointwise tropicalization. And the claim is that this set theoretically defined map is in fact a tropical map. It respects integral affine structure. It's a piecewise integral affine map. But not only that we have such a map, it satisfies certain properties over the two types of cones that we discussed. The first type is the nice cones. And the claim essentially says the following: you have harmonicity at vertices that are mapped to nice cones. In other words, if you look at the image of the tropicalization of the base inside a nice cone in the moduli space, it looks like a tropical curve. It's a balanced curve. Okay, it's not just some one-dimensional object, it's a balanced curve. So balanced is something very rigid. It allows you to have a very good control on how it can look inside a nice cone. Okay. The second property tells you the following: if a vertex of the base get mapped to a simple wall, to the simplest possible degeneration of nice cones, okay, then there are two possibilities. Either the map alpha is harmonic at this vertex too, and the whole star of this vertex get mapped to this nice cone. This is one possibility. Or it is locally combinatorially surjective, and this means that the star of the vertex W in the tropicalization of the base is mapped surjectively onto the star of the simple wall. In what sense mapped surjectively? So each nice cone, you have three nice cones attached to a simple wall. So there is at least one ray in the star of W that get mapped to a given cone attached to the simple wall. Okay. So in here is a cartoon. So if M chi is a simple wall, and we have three nice cones on the right, this is a cartoon of three nice cones attached to the simple wall. And we have on the left, we have a vertex W of the base curve, over which we have a curve that gets mapped, the fiber whose isomorphism class belongs to this M chi. Okay, it has a unique four-valent vertex. And the claim is that the tropicalization of the base, so we have here, we have only three rays, we could have more rays, but for each one of the three cones, nice cones attached to M chi, we have at least one ray that alpha maps to this cone. Okay, this gives you the second ingredient that allows you to control the image of alpha inside the moduli space. In a sense, if you travel from a nice cone along the image of alpha and you hit a simple wall, you can proceed to either of the other two nice cones that resolve this simple wall, okay, that are attached to this simple wall. To each one of them, you can choose the one you want to proceed to, and you can proceed. So in other words, there will be points in the base of my family, fibers over which will belong to M theta for given theta. Okay, so this is the game that we are going to play in the proof of the main result. Okay, so let me just mention that in fact tropicalizations of families of curves, they are well studied in several settings: in log setting, in non-log setting, for high dimensional families. So this is a rather active business. So there are works of Ranganathan, of Cavalieri, Chen, Ulrich, and Weiss that develop these things for their own purposes. Okay, in different categories. So some things work only in characteristic 0, some are general, some require your family to be log smooth, some do not, and so on and so forth. So there is a variety of results on tropicalizations of families. So for the sake of this talk, it is sufficient to consider this most naive tropicalization in the one-dimensional case, okay, in the one-parameter case. Good. So now we have about 20 minutes, and we are ready to start the proof by example. These are my favorite proofs. So let us see the example. So the example is a.
Can you please, can I ask something? Can you explain intuitively why do you need the covering of the base in the tropicalization result? What does that achieve?
Yes, I can. The reason is the following. If you start with just a family like this, and you don't assume anything on the fibers, then you don't have the notion of tropicalization of a fiber, you don't have the notion of tropicalization of the base. So you want to replace your family with a stable family so that it will be generically smooth, okay? And over some points of B, it will degenerate, okay? To achieve this, you must do some finite covering. You must do some alteration on the base. In the case of curves, it is just a finite covering. And then you can achieve a model of your family, okay, such that both the base is smooth, the fibers are generically smooth, and those that are not smooth, they are stable, okay? So in a sense, this is something you must do in order to pass to log smooth setting where the tropicalization works most naturally, okay?
Okay, so you just needed to define the set map, not to get the nice properties of it.
Yes, that's true. But notice, since it's a finite covering, so the fibers, the set of fibers is the same set of fibers. So if I show that after this finite covering, I have a fiber with certain properties, then I had it from the very beginning. Okay.
Yeah, thanks. Got
it. Okay, so this is the example. So in this example, we consider a weighted projective plane. So it's unlike in the statement of the theorem where all surfaces were smooth. Here I consider a non-smooth surface to show that in fact this technology works for a larger class of surfaces. And it is the surface associated to the lattice triangle with vertices 0, 0, 4, 1, and 0, 3. Okay, this is a picture. So you have 4 inner integral points. So in this case, the arithmetic genus of the linear system prescribed by this triangle is 4. And the actual geometric genus that I'm going to fix is 2. Okay. So in other words, a general curve parameterized by the severe variety in this case will have total delta invariant 2, and one can prove, it's not very difficult, that it will be binodal regardless of the characteristic. Even if the characteristic is 2 or 3, general curve C in V delta 2 will have 2 nodes. Okay, it requires, it's not obvious. And there are surfaces where this is not true in positive characteristic, but in this case, it doesn't matter what characteristic you are in. The general curve in V delta 2 here will be binodal. Okay, good. So now our goal is to prove that this variety, this particular variety, is irreducible. Okay, that you have an irreducible family of curves of this toric degree and genus 2, geometric genus 2. So let me remind you the strategy of the proof. So what was our strategy to start with? So the strategy was the following. So first, you want to find a combinatorial type theta naught that belongs to, that is liftable to curves in a uniquely defined irreducible component. In other words, there is a unique irreducible component in the severe variety that admits curves whose tropicalization have type theta naught. This is the first step. And the second step, to show that any irreducible component must contain such curves. And to prove the second step, we will need this game, this control over images of certain one-parameter families of curves inside the tropical moduli curves of given degree and genus. Okay, so here is the first step. So let me draw a picture, an explicit picture. So the following parameterized tropical curve admits a lifting to a unique irreducible component. So I draw here the dual subdivision and the actual curve. You can notice that this is a floor decomposed curve, and in fact, all curves I will consider today will be in the rest of the proof. They will also be floor decomposed. Okay, and on the right we have the dual subdivision defining this curve. Okay, so now I will not prove this lemma. The proof is deformation theoretic. So in a sense, what you have to do, you have to show that the so-called tropical reductions associated to the space of tropical reductions associated to this curve is irreducible, and the deformation space that allows you to reconstruct the algebraic curves from their reduction is in this case unobstructed. And this is how the proof works. Okay, once you have these two ingredients, you can prove that there exists unique component of the severe variety to which such tropical curves admit a lifting. Okay, so this is the idea of the proof, but this is a very explicit lemma. So let me also give you some flavor, maybe that will explain why you would expect this curve to be liftable to a unique component. The reason is that this is a multiplicity 1 curve. Okay, so if you're familiar with Michalkin's enumeration, then these all triangles here have area 1/2, so integral area 1, and the Michalkin's multiplicity in the enumeration is 1. Okay, and this gives you an indication that in fact, when you compute the degree of the severe variety, you count this curve once, and the reason you count this curve once is that it lifts to a unique component. Okay, again, it's not a proof; it's just some indication why this works. But I hope that it gives you some intuition why this works. Okay, and now what I would like to show that in fact any irreducible component necessarily admits curves, contains curves whose tropicalization looks like this. Okay, this will complete the proof. This will be proof step 2 and will complete the proof of the main result in this particular example. Okay. Okay, good. So now pick any irreducible component, and it remains to show that this particular type belongs to the set of combinatorial types associated to it. So how do we prove it? We must start with something. We must find some type that belongs to CTV. So to do this, we pick 7 points in the surface as delta, but in such a way that their tropicalizations are vertically stretched. And once they are vertically stretched, this tells me something about the tropicalization of a curve in V that passes through these 7 points. So first notice that since the dimension of the severe variety, well, this is a direct computation, the dimension is 7, like the number of constraints that I imposed. And my constraints are general. There is some curve C in V that passes through these points. Okay. So I have something to start with, and I can look at its tropicalization. Due to the result of Bruegel and Michalkin, I know quite a lot about its tropicalization. So its tropicalization is floor decomposed. It is weightless. Okay. It passes through these 7 points. It is regular. It is trivalent, and so on and so forth. So it is rather nice. So in particular, the combinatorial type of the tropicalization of C is a nice type. Okay. So now here is the cartoon of 5 possible floor decomposed curves that can pass through 7 of genus 2, that can pass through 7 points in vertically stretched position and have the degree dual to the triangle. Okay, so we must have 3 floors. Okay, let me maybe explain here. We always will have 3 floors. Okay, 1, 2, and 3. Okay, so we must have 3 floors. The genus must be 2. And now if you play with the balancing, you see that these are all the possibilities, and the bottom left possibility is the one that we want to achieve. Okay, we want to show that any reducible component must contain curves of this type. What we know from start, we know that at least one of these types is the tropicalization of a curve in my component V. And for the sake of concreteness, I will assume that this is the bottom type on the right. Okay. In fact, it is the most complicated case. So the rest cases, the other 3 cases, you can check directly along the same lines, and it will be easier. Okay. So I will assume that the tropicalization of the curve C that I constructed in my reducible component V looks like the type on the bottom right, and they will try to convince you that there is another curve in V that has type like in bottom left. So far, so good? Okay, good. So now we start playing the game. So there are no more words on my slides, only pictures. So I start, this is on the left, this is the picture. By the way, I didn't mention this, but these numbers 2, 3, and so on, they indicate the multiplicity of the edge, okay? The integral lengths of the slope, okay? So it can be 1, then I don't write anything, 2 or 3 in these cases, okay? So here is on the left, I have the picture of type, of the bottom right type. Okay, I have multiplicity 2 edge joining the top floor with the second floor, multiplicity 2 edge joining the second floor with the third floor, with the bottom floor, and I have 2 multiplicity 1 edges. And the first thing I do, I distribute points. In fact, in this way, I obtain this curve. So I distributed these points, and this was the tropicalization of the algebraic picture. So the first thing I do, I release this point that I show with the cursor. Can you see what I show? Okay, good. So I release this point. And now I obtain, on the algebraic side, I obtain a 1-parameter family of curves. If before that I impose 7 conditions on independent conditions on a 7-dimensional variety and reduce the dimension to 0, I released 1 point, and now I have a 1-parameter family of curves on the algebraic side inside my reducible component of the Severi variety. And its tropicalization, so this is a particular fiber, this is a particular, the second curve, this is a particular fiber of its tropicalization. Now, the tropicalization on the tropical side inside the modular space, it moves in a 1-parameter family. But you can see that this curve, the only movement it has, you can move this free elevator right and left and change the floors accordingly to get something balanced, okay? So inside this nice cone in the modular space, I have a straight interval along which my curves can move. So the image of the tropicalization sits inside a straight interval, but it must be a tropical curve. We discussed it, that harmonicity property ensures that the image of alpha of this map from the tropicalization of the base to the modular space inside a nice cone looks like a tropical curve. It is balanced. So if it sits inside an interval, it's either a single point, which it is not, or it is just the whole interval. There are no other possibilities. So this means that I can start moving this elevator to the left, and all such curves will be realizable in my 1-parameter family that sits in my irreducible component of the Severi variety. So in particular, we move this elevator to the left till it meets this marked point, passes it, and hits the simple wall parameterizing curves with 4 valent vertex here. Okay, this is a simple wall. Now we apply local combinatorial surjectivity. If we hit a simple wall with a 1-parameter family from one nice cone, there are rays in the same one parameter family, the tropicalization of the same one parameter family, that exit to either one of the two other nice cones adjacent to this simple wall. And the possibilities are the following. We can either continue moving this bottom half to the left, or we can separate the upper half with the bottom half of the elevator from the two edges of the floor here. And this is illustrated in the next picture, okay? So this is a picture that represents another nice cone adjacent to the same simple wall. And we know that such tropicalizations are parameterized by curves in my one parameter, okay? So we continue. Again, this is a nice cone. This is a nice type. It is trivalent. It has expected dimension. It is weightless and so on and so forth. Inside nice cone, the image of alpha, the image of my base of the tropicalization, sits inside a straight interval, so it must coincide with this straight interval. And this means that nothing can stop me from continuing deforming this, moving this trivalent flattened vertex to the top till I hit the next wall and I get this four-valent vertex, okay? And again, it has two possible exits. One is joining this long elevator with the left half of the floor and another with the right half of the floor, and I prefer to join it with the left half of the floor. This is indicated in this last picture, okay? So you see that I started with a curve, which was a tropicalization of some curve in my component. I knew essentially nothing about the component, and I managed to prove that the same component necessarily contains curve with tropicalization, like on the right, and this tropicalization looks much more like the curve you want to achieve, right? Kind of it remains to get rid of this multiplicity 2 elevator here, and we will be done, okay? So now we do the following. We release all these points, and we fix elevators as we wish, and I wish to move this point from the right top elevator to the left top elevator. And I am free to do it. And now I get a new one parameter family that starts from the algebraic curve with this tropicalization that satisfies the algebraic constraints where this point jumped here. So, and here is the picture. This is what happens. This point jumped here, okay? And again, I play the same game. I get a new one parameter family on the algebraic side that entirely sits inside my irreducible component that a priori I knew nothing about. But I know that it contains a curve with such tropicalization, okay? So I can play the game and look what other tropicalizations my CTV must contain. And here we start moving this top elevator to the right, okay, till it hits this marked point, and it proceeds till we hit we get these two elevators get joined, so we get a simple wall with four-valent vertex. And this one, well, this time I want to resolve it like this. I want to keep moving the top half of the elevator to the right, okay, till it hits next elevator, this double elevator goes down. This is the next picture. And only now I start traveling with the elevators, okay, along the bottom elevator. I take this simple wall with four-valent vertex that corresponds to this picture. And I choose this resolution where the two elevators get joined together and the two edges of the floor get joined together. I get a new nice cone, and I know that such a curve is the tropicalization of a curve in my original irreducible component. I can, again, in this nice cone, okay, the image sits inside the straight interval, okay? So it must coincide, the image of the base of the tropicalization sits inside straight interval. It must coincide with the straight interval. So I can proceed deforming till I hit this bottom vertex. This is indicated in this picture. And then I resolve this simple wall, this 4-valent vertex. In this way, I move my elevator to the left. So this is almost what I wanted. It remains to keep moving it to the left till I get this picture. And this is the original picture I wanted to arrive at. Okay. So what we did, we started with some floor decomposed curve that was a tropicalization of a curve in a given irreducible component that we knew nothing about. Okay. Due to Bruegel and Michalkin, there is such an algebraic curve there with floor decomposed tropicalization. And then we started playing game with the two properties in the tropicalizations of one-parameter families, and considering different one-parameter families of curves prescribed by imposing various 6-point constraints, till we managed to show that the same irreducible component V, the set CTV of combinatorial types associated to V, necessarily contains this curve. And since we know that there is only one component such that CTV contains this curve, this completes the proof of the irreducibility. Okay, so this is all I wanted to tell you. So thank you very much for your attention. If there are any questions, I will be happy to answer.